Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargava. Under Transferred Electron Devices, today we would be studying about high field domains. After the observation of microwave oscillations in the N-type gallium arsenide, various modes of operation have been developed depending on material parameters and operating conditions. So what we are saying is, after observation of microwave oscillations in N-type gallium arsenide, which we talked about in Gunn effect, various modes of operation have been developed depending on material parameters and operating conditions. So there are different modes of operation, and what do they depend upon? They depend upon material parameters and the operating conditions. The formation of a strong space charge instability depends on the conditions that enough charge is available in the crystal and the specimen is long enough to build necessary amount of space charge within the transit time of electron. So what are the conditions required to build a strong space charge instability? That would be decided by that crystal has sufficient charge. Secondly, the specimen is sufficiently long enough so that space charge can build up during the length of the specimen when it travels within transit time of the electrons. This requirement sets up a criteria for various modes of operation of bulk negative differential resistance devices. So these things, that is the length of the specimen, the transit time, and the nature of or availability of space charge, these are the three things which would decide the criteria for various modes of operation. Copeland proposed four basic modes of operation during doped bulk diodes with low resistance contacts as shown in the figure. So he suggested four basic modes, which are Gunn oscillation mode, stable amplification mode, LSA oscillation mode, bias circuit oscillation mode. So let us pick up one by one. All these are shown here. This represents the quenched domain, transit time domain, the delayed domain. So all of them decided on the basis of the product FL and the product N0L. These are the two critical numbers which would help in modes of classifying the modes of operation for Gunn diodes. Now let us find out what are the criteria for classifying the modes of operation. There is a criteria whether the domain is allowed to propagate or not, allowed to form at all. So we are saying there is a criterion whether the domain is allowed to propagate or not. एक ऐसा क्राइटेरिया जिसके अनुसार डोमेन क्या क्रिस्टल या मटेरियल में प्रोपोगेट कर पाएगी या नहीं, या दूसरा पार्ट है बन ही ना पाए, not allowed to form at all. During the early stages of space charge accumulation, the time rate of growth of space charge layer is given by. In the earlier stage of the space charge accumulation, the time rate of growth of space charge layer is given by the equation Qxt would be equal to Qx minus Vt 0. So Q represents something that is the space charge at time t and position x. And what does it depend upon? Space charge at the time t is equal to 0 and at an earlier position x minus Vt e power minus t upon Ct, where tau d T upon tau d. Tau d is epsilon upon sigma. Epsilon upon E n0 mu n is magnitude of negative relaxation time. In this equation, epsilon represents semiconductor dielectric permittivity. E represents the electron charge. N0 represents the doping concentration. And mu n represents the negative mobility and sigma represents conductivity. So the various letters that have been used in this equation have been explained here. Epsilon for dielectric permittivity, E for the electron charge, N0 the doping concentration, mu n the mobility, and sigma the conductivity. The factor of maximum growth for the domain is, growth factor is given by Q, L or L by V upon Q00 is equal to exponential L upon V tau D, and this can be written as exponential L N0 E mu n upon epsilon V. The layer is assumed to start at cathode, that is at t is equal to 0 and x is equal to 0. So the layer is supposed to start and the initial time taken is t is equal to 0, the initial position coordinate is x is equal to 0, and is supposed to arrive at anode from cathode to anode at that, and how much time does it take to reach anode? T would be equal to L upon V and x is equal to L. For large space charge growth, this factor must be larger than unity. If I require large growth of space charge, then this factor has to be greater than 1, or N0L is greater than epsilon V upon E mu n. Now we have the value of epsilon as 13.1 into 8.854 into 10 raised to the power 12 minus 12. V would be 10 raised to the power 7 centimeter per second. The mobility mu n would be equal to 100 centimeter square per volt per second, and for n-type semiconductor, that is gallium arsenide, the product N0L should be greater than 10 raised to the power 12 per centimeter square. Now we pick up Gunn oscillation mode, where N0L must be greater than 10 raised to the power 12 per centimeter square and must be less than 10 raised to the power 14 per centimeter square. In the Gunn oscillation mode, the range of N0L is given by 10 raised to the power 12 per centimeter square less than N0L must be less than 10 raised to the power 14 per centimeter square. When N0L is greater than 10 raised to the power 12 per centimeter square in gallium arsenide, the space charge perturbation in the specimen increases exponentially. So if you want a space charge to increase, then N0L must be greater than 10 raised to the power 12 per centimeter square. The space charge perturbation increases exponentially in space and time as given by Qxt is equal to Qx minus Vt0 e power t upon tau d. A high field domain is formed and moves from the cathode to anode under this condition. The frequency of oscillation is given by F is equal to V domain upon L effective, where V domain is the domain velocity and L effective is the effective length that domain travels from the time it is formed until the time a new domain begins to form. So what is V domain? It is the velocity by which the domain travels, and L effective is the length that the domain would travel from the time it is formed to the time the next domain is about to be formed. The normal Gunn domain mode or Gunn oscillation mode is operated with electric field greater than the threshold. So here, if you want to have normal Gunn domain mode, the electric field applied should be greater than the threshold field. The high field domain drifts along the specimen until it reaches the anode. So high field domain, it starts its movement from the cathode and continues to move till it reaches anode or until the low field value drops below the sustaining field Es required to maintain Vs as shown in the figure. Or the second condition is until the low field value, that means the field drops below the sustaining field Es to maintain Vs as shown in the figure. The sustaining drift velocity for gallium arsenide is Vs equals 10 raised to the power 7 centimeter per second. So this represents the sustaining field, this represents the threshold field. So whenever threshold field से ज़्यादा field लगाएंगे तो क्या होगा, डोमेन फॉर्मेशन आ जाएगा. और डोमेन ड्रॉप आउट कब होगी, when the electric field is below this critical value of ES. Since the electrons drift velocity V varies with the electric field, so there are three possible domain modes for the Gunn oscillation mode. Now what does this show? The drift velocity is changing with respect to the electric field. On this axis you are plotting electric field, and on this axis you are plotting drift velocity, and we find drift velocity changes with respect to the electric field. So this generates three modes of oscillation. The first one is the transit time Gunn domain mode. In this mode, F into L is nearly equal to 10 raised to power 7 centimeter per second. When the electrons drift with velocity Vd, when the electron drifts, velocity Vd is equal to the sustaining velocity Vs, the high field domain is stable. Drift velocity is equal to the sustaining velocity Vs, then high field domain remains stable. The electron drift velocity Vd is given by Vd is equal to Vs is equal to Fl, and that is 10 raised to power 7 centimeter per second. So this is transit time. In this case, the period of oscillation tau 0 is equal to the transit time tau L. So tau 0 equals tau L. Figure A shows this situation. So this represents here the figure A. This represents the figure A here. Here tau 0 equals tau L. This represents the DC bias. This represents the threshold field. This represents the sustaining field. This is transit time mode. Here the efficiency is below 10% because the current is collected only when the domain arrives at the anode. The value of N0L for this mode is 10 raised to power 12 centimeter square. The resonate frequency of the resonate circuit is equal to the transit time frequency for this mode. So when I say transit time mode, tau 0 would be equal to tau L. Efficiency is relatively less because the current is collected only under one condition, when the domain reaches the anode. Here the value of N0L for this mode is 10 raised to power 12, and the resonance frequency of the resonate circuit is equal to the transit time frequency for this mode. Now we have delayed domain mode. If the time period tau 0 of the signal in the resonate circuit is greater than the transit time tau L, the domain for E less than the threshold field is collected early in the negative half cycle of voltage as shown in the earlier figure B. Just see here. This represents figure B. So this is here tau 0 is greater than tau L. Just see, from this place it is tau 0 greater than tau L. So here it is collected before, and that is why is collected early in the negative half cycle of the voltage. The new domain cannot form until the field rises again above the threshold value ETH. This is called delayed domain mode or the inhibited mode. For this mode, FL lies between 10 raised to power 6 to 10 raised to power 7 centimeter per second. FL is greater than 10 raised to power 6 centimeter per second but less than 10 raised to power 7 centimeter per second. And here tau 0 is greater than tau L. Here efficiency of this mode is around 20% larger than the first case. This mode is advantageous because the frequency of oscillation can be varied by resonance circuit and can be tuned over a wide frequency band up to 1 octave. So efficiency is more. This is advantageous because the frequency of the oscillation can be changed by the resonance circuit. So you can change the frequency. That is an additional advantage. The third one is the quenched domain mode, that is figure C. In this mode, the DC bias field E falls below the sustaining field ES during the negative half cycle. The domain collapses before it reaches the anode. तो एनोड पर पहुंचने से पहले ही डोमेन खत्म हो जाती है. A new domain is initiated only when the bias field goes above ETH. Then the process is repeated. This is called quenched domain mode. In this case, tau 0 is less than tau L. Frequency of the oscillation can be several times the transit time frequency. For this mode, FL is greater than 2 into 10 raised to power 7 centimeter per second and the efficiency is up to 13%. This mode is tunable over a broad frequency range. So, the three modes that differ on the basis of FL. At one place, that is the normal mode, it was 10 raised to power 7 centimeter per second. Here in the quenched mode, it is FL which is greater than 2 into 10 raised to power 7 centimeter per second. And in the second mode, which was called as the delayed mode, there FL was supposed to be between 10 raised to power 6 centimeter per second to 10 raised to power 7 centimeter per second. So that is how we classify the three different modes in under Gunn oscillation mode. The next one that we pick up is limited space charge accumulation, that is the LSA mode. When the microwave signal frequency and the amplitude are very high, the domains do not have enough time to form while the field is above threshold. Now what are we saying? When the microwave signal frequency and the amplitude are very high, domains do not have sufficient time to form while the field is above threshold. In this case, most of the sample lengths are maintained in the negative conductance state during a large fraction of the voltage cycle. So, in the LSA mode, what we are trying to do is here when the microwave signal frequency and the amplitude become high, the domains do not find sufficient time to form till the field is above threshold. अभी तक हमने क्या पढ़ा था? डोमेन फॉर्मेशन कब होगा? जब when the field is greater than the threshold. और यहां पर क्या हो रहा है? जब तक फील्ड थ्रेशोल्ड से ज्यादा है तब तक डोमेन के पास डोमेन बनने का सफिशिएंट टाइम ही नहीं है. In this case, most of the sample lengths are maintained in the negative conductance state during a large fraction of voltage cycle. तो हम क्या करते हैं? Sample length is maintained at negative conductance state. Any accumulation of electrons near the cathode has enough time to collapse while the signal is below the threshold. तो जो आपके पास में इलेक्ट्रॉन्स कैथोड के पास थे वो कोलैप्स होते हैं कब? जब सिग्नल थ्रेशोल्ड से नीचे होता है. दिस मोड इज कॉल्ड लिमिटेड स्पेस चार्ज अक्यूमुलेशन. इसीलिए स्पेस चार्ज अक्यूमुलेशन पहले जैसा नहीं हुआ. इट इज जस्ट अ लिमिटेड पार्ट ऑफ स्पेस चार्ज अक्यूमुलेशन दैट इज टेकिंग प्लेस. क्योंकि बहुत सारा चार्ज जो कैथोड के पास है वो कोलैप्स हो जाता है क्योंकि सिग्नल तब भी थ्रेशोल्ड के नीचे रहता है. And it is the simplest mode of operation. LSA mode is the simplest mode of oscillation. It consists of a uniformly doped semiconductor without any internal space charge. The internal electric field is uniform and proportional to the applied voltage. यहाँ पर क्या हो रहा है? इन सब के लिए हमें क्या चाहिए? इट कंसिस्ट ऑफ अ यूनिफॉर्मली डोप्ड सेमीकंडक्टर जिसमें कोई इंटरनल स्पेस चार्ज नहीं होगा. द इंटरनल इलेक्ट्रिक फील्ड कैसा है? यूनिफॉर्म है एंड इट इज प्रोपोर्शनल टू द अप्लाइड वोल्टेज. द करंट इन द डिवाइस इज प्रोपोर्शनल टू द ड्रिफ्ट वेलोसिटी एट दिस फील्ड लेवल. इस फील्ड लेवल पे करंट is proportional to the drift velocity. The efficiency of the LSA mode can maximum reach to 20%. The LSA mode requires that the period tau 0 of the resonant circuit should be no more than several times larger than the magnitude of dielectric relaxation time tau d in the negative conductance region, but should be much larger than tau d for low conductance region, so that any accumulation of the electrons will collapse while the signal is below threshold. So once again let us see what does LSA mode require. It requires tau 0 to be no more than several times larger than the magnitude of dielectric relaxation time. Tau 0 should not be very large as compared to tau d in the negative conductance region, but should be much larger than tau d for low conductance region. So there are two conductance. Low conductance region के अंदर tau 0 must be very much greater than tau d, और negative conductance region के अंदर tau 0 should not be very much greater than tau d. ये हमें क्यों चाहिए? So that any accumulation of the electrons will collapse while the signal is below threshold. ताकि सिग्नल जब तक थ्रेशोल्ड के नीचे है तो वो इलेक्ट्रॉन वहीं पर कोलैप्स हो जाएंगे. दिस मोड इज शोन इन फिगर डी इन विच tau 0 is equal to 3d. For n type gallium arsenide, the product of doping in N0L is about 10 raised to power 12 per centimeter square. So देखिए यहां पर फिगर डी, ये आपका LSA mode. Tau 0 is less than tau L and tau 0 is 3 times tau L. So यहाँ पर आप देखिए this represents the sustaining field, this represents the threshold field and this represents the applied DC bias. So at the low frequency limit, the drift velocity is taken as VL is equal to FL, which is 5 into 10 raised to power 6 centimeter per second. The ratio N0L to FL gives N0 by F is 2 into 10 raised to power 5. At the upper frequency lift, the drift velocity V upper is equal to FL, which is 5 into 10 raised to power 7 centimeter per second. And the ratio N0L to FL is N0 by F is 2 into 10 raised to power 4. तो अपर फ्रीक्वेंसी लिमिट में वैल्यूज अलग हैं और लोअर फ्रीक्वेंसी लिमिट में अलग हैं. बोथ अपर एंड लोअर बाउंड्रीज ऑफ LSA मोड आर इंडिकेटेड इन फिगर 1. तो अपर एंड लोअर बाउंड्रीज आर वंस अगेन शोन इन द फिगर 1. हम उस वापस से चलते हैं वहां. ये देखिए ये दोनों बाउंड्रीज यहां पर ऑटोमेटिकली शो कर रखी है हमने. करेक्ट. Now let us pick up the next topic as stable amplification mode, where N0L is less than 10 raised to power 12 per centimeter square. Up till now N0L was either equal to 10 raised to power 12 or greater than 10 raised to power 12. Now we have less than 10 raised to power 12 per centimeter square. When the N0L product of the device is less than about 10 raised to power 12 per centimeter square, the device exhibits amplification at transit time frequency rather than spontaneous oscillation. तो यहाँ पर स्पॉन्टेनियस ऑसिलेशन की जगह एम्प्लीफिकेशन देखने को मिलेगा. दिस इज पॉसिबल बिकॉज द नेगेटिव कंडक्टेंस इज यूटिलाइज्ड विदाउट डोमेन फॉर्मेशन. Normally there are very few electrons available for the domain formation in the transit time. Therefore the amplification of signal near the transit time frequency can be done. तो हमने क्या बोला है, ये पॉसिबल क्यों है ऑसिलेशन की जगह एम्प्लीफिकेशन? दिस इज पॉसिबल बिकॉज द नेगेटिव कंडक्टेंस इज यूटिलाइज्ड विदाउट डोमेन फॉर्मेशन. डोमेन फॉर्मेशन में यूज नहीं कर रहे हैं हम. नॉर्मली देर आर वेरी फ्यू इलेक्ट्रॉन्स अवेलेबल फॉर द डोमेन फॉर्मेशन इन द ट्रांजिट टाइम. पूरे ट्रांजिट टाइम के अंदर डोमेन फॉर्मेशन के लिए इलेक्ट्रॉन अवेलेबिलिटी बहुत कम है. इसीलिए एम्प्लीफिकेशन ऑफ सिग्नल नियर द ट्रांजिट टाइम फ्रीक्वेंसी कैन बी डन. There are many types of amplifications depending on FL product of the device as shown in this figure. तो बहुत सारे amplifications यहाँ पर possible हैं. जैसे हमने मार्क किया ना, ये फर्स्ट amplification, सेकंड amplification, थर्ड amplification. The various modes of operation of Gunn diodes can be classified on the basis of times in which various processes occur. These are defined as tau L, the domain transit time, tau G, domain growth time, tau D, dielectric relaxation time at low field, tau 0, natural period of oscillation of a high Q, external electric field. The modes described earlier are summarized in this table. All the modes that have been described till now are summarized. This is transit time or the resonant Gunn mode. Here tau 0 would be equal to tau L. FL would be 10 raised to power 7 centimeter per second. It has an efficiency 10%. Non-resonant frequency determined by transit time and low quality factor. Then we have delayed domain or inhibited mode. Tau 0 is greater than tau L. 10 raised to power 6 से 10 raised to power 7 सेंटीमीटर पर सेकंड के बीच में FL है, but the efficiency is around 20%. Resonate high Q mode. Quenched domain mode. Tau 0 less than tau L. 10 raised to power 6 से 10 raised to power 7 centimeter, but the efficiency is 13%. It is also resonate and high Q mode. Limited is space charge accumulation or the LSA mode. Tau 0 is less than, very much less than tau L, and tau L is equal to 3 tau 0. So FL is 5 into 10 raised to power 6 less than 10 raised to power 7. Efficiency is 20%. Multiple resonate mode. 2 into 10 raised to power 4 less than N0 by F is less than 2 into 10 raised to power 5. Upper and lower frequency is described properly here. Stable amplification mode. N0L must be less than 10 raised to power 12 per centimeter square, and FL to have value between 10 raised to power 7 to 10 raised to power 8. Efficiency quite small, 2 to 3%. The transit time, frequency independent of sample length. So I think the different modes of operation have been clearly explained to you all. अगर आपको हमारे वीडियो अच्छे लगते हैं तो लाइक करिए, कमेंट करिए, चैनल को सब्सक्राइब करिए ताकि आपको नए वीडियो का नोटिफिकेशन टाइम पर मिल जाए. थैंक यू वेरी मच.